Okay, any questions before we get started today? So we're going to do some problem solving, putting it all together. We're given the different pieces of data. And then we want to come up with a structure from all those pieces. Make sure that it's self-consistent and we're not sort of contradicting any of the information we're given. We'll also look at the reason why proton NMR signals form these doublets, triplets, quartets, what is happening in that case. And so we'll talk a little bit about that information, why they look the way they do, why they have those intensities. And I guess next week is your spring break. So we'll finish this module the Monday after. And on that day, we'll talk about what's known as the actual coupling constant. So within a say a doublet or a triplet, you have this separation of those lines. We'll measure what that distance is based on the y-axis or the x-axis measurement. And we'll see that that distance information tells us a certain relationship to the neighbors. And that sort of forms a thread into Module 3. So I thought we would start off. We've learned quite a bit so far. We've taken our Lewis dot structures. We've learned about functional groups. And so we've seen IR, mass spec, proton, and carbon NMR. And so I have a book that has about 200 of these problems. So I screen grabbed the data from one of those problems, and we'll walk through it. And so, I mean, this is the information you're given. And from that, you're asked to propose a structure. And what you'll find is that once you sort of know what to look for, you'll see a lot of the things reinforce the information from one piece of spectral information to another. So we'll just start off. We'll look at IR, then the mass spec, then the carbon. There's one new thing in the carbon I want to point out to you, and then by the time we get there, you'll see that the proton should fall into place, basically. So in the IR spectrum, make sure everyone can see that like I see it. Okay, so we're given a couple pieces of information. It says 3,500 to 2,500 and then 1,715. So there's two clues there, and based on those two clues, does anyone know what major functional group those signals belong to? Carboxylic acid. So we see this signal here. So that's our region 3. And that's a pretty intense signal. You can see it almost goes down to the x-axis. And we can say that belongs to a carbonyl group. And then in region 1, we look at this very broad. And again, when I say broad, I'm looking at where it starts to dip down. And then the span over in wave numbers. It's a very broad signal. And the way that looks, that's due to an OH, and that OH is attached to a carbonyl. So that's another fragment. So overall, from the IR, we can piece together this fragment. So a carboxylic acid. And so that's equivalent to CHO2. So we're slowly building up a molecular formula. The other thing we can point out about this, the carbonyl group is 1 degree of unsaturation. The carbon, because it's a carbonyl, is sp2 hybridized. And this post-it note that you see right here, that gives you the molecular formula. I covered it up so that we can go through and just figure it out by ourselves. So we're off to a start here. In the mass spec, see the parent ion M+, it says 74. That's an even number. So what can we say? There's no odd number of nitrogen atoms. The other thing you'll note, you don't really see any M+2. So there's nothing there that says 76. So we can rule out chlorine and bromine. So we have this even mass. We've ruled some things out. That helps us in terms of our claim, because now we don't want to draw anything that has N, Cl, or Br in it. So let's move over to the carbon NMR now. Notice the bottom part says proton decoupled. That's the standard way that a carbon NMR looks. There's solvent. The solvent is just the liquid you dissolve your sample in. And because that liquid is a chemical, it can also have some carbons that are measured, and we don't consider that. It's just there, it's labeled. So aside from that solvent, how many signals do you see in that bottom carbon spectrum? 3. So that's 3 unique carbons. So we have 2 of them between 0 and 40, and then 1 of them at 180. The one at 180 belongs to what? So this is the sp2 hybridized carbon. The 2 between 0 and 40 are what hybridization? sp3. Because they're sp3, what that's also telling you is they're fully saturated, right? So at this point, you have 3 carbons. I mean, you can bond them together and you're going to get the structure. So we won't just do that just yet. Let me point out some other things and you'll see how this ties into the proton. So in the carbon NMR, there's a plot above. So this is a stack plot, and it says DEPT, D-E-P-T. And there's this key. It says CH2 down, CH3, CH up. So if the line here, that's your sort of baseline. If you see a signal up, that's phased positive. If you see a signal down, it's phased negative. And what the key is telling you that the signal that's down, that's what this little arrow here means in the key. That's a CH2 group. Notice it's stacked right above one of the other signals here. So it's stacked right above that. So that tells you that is a CH2 group. So that's another fragment. Then the other signal, it's positively phased. So it's CH or CH3. And say at this point, we weren't certain about what it was. Then we could go to the proton NMR. So notice in the proton, it has this thing between or around 11 parts per million. It says exchanges with D2O. We already determined from the IR, we have an OH of the carboxylic acid. So what the proton NMR is telling us, that H exchanges with deuterium. So the solvents that you run these samples in are deuterated solvents. They have to have a deuterium label so that you're not getting swamped out by the hydrogens of the solvent itself. So that's what that thing is. Notice it's a broad singlet. There's no splitting because there's no neighbors. So other than that, how many sets of hydrogens do you see in the proton NMR? So we see 2 unique sets. Then I have these numbers written in blue that say 8 and 12. If you notice, see this curve here? Like back in the day when, like in, earlier NMR experiment, that was called an integration curve. And so all I did was take a ruler and measured the distance from the bottom to the top of that curve in millimeters, and I got 8 and 12. So we're going to use the information to set up a ratio. And then this is sort of like a Gen Chem problem. From that ratio, we're going to figure out the attached, or the number of hydrogens that belong to that signal. So we have 8, we have 12. And so the common denominator for those would be 4. So I'm going to put up here, divide by 4. So then we get 2 and 3. And so that tells you this is 2 hydrogens, and this is 3 hydrogens. So now we can go back up into the carbon NMR and say that that positively phased signal belongs to a CH3 group. And so we now have 3 fragments. Carboxylic acid, a methylene group, and a methyl group. So how should we bond those together to make a structure that's consistent with Lewis dot rules? So the carboxylic acid will be the terminus, then we'll bond one of the methylenes to that, and then the other side of the methylene becomes the methyl. So overall, we end up with this 3-carbon acid, so that would be called propanoic acid. So the other thing I want to point out, I'll redraw the structure down here. So let me call this, we kind of already know, but I just want to verify, A and B. We know that A is 3 hydrogens, so we can make the assignment there. B is 2 hydrogens, so we can make that assignment. I know it's tough to see, but when you look at the signal for A, can you figure out what its multiplicity is? Singlet, doublet, triplet, quartet. So it's going to be a triplet, and we'll just represent that as small t. So it's a signal that integrates to 3 hydrogens. It has 2 neighbors, so it appears as a triplet. So B should be what? A quartet. So B integrates to 2 hydrogens. It has 3 neighbors. We apply the n+1 rule, so it's a quartet. And, my advice, when you're practicing these problems is try to make sure that your argument is self-consistent. Point out as much detail as you can in describing things so that you're not leaving a hole that could potentially lead to ambiguity somehow. And again, the relevance of this is when you get a prescription filled from your doctor, you're operating under the trust that that pill is exactly what, the drug is saying it is, what indication it has, not some other isomer or something completely different. So the spectral data is the way we image organic compounds in a way that's the visual way we see the data that represents the molecule. Now we tie everything together and come up with a claim, and we make that claim as bulletproof as we can so that there's no doubt about what it is. Any questions on that? So we'll spend the next little bit of lecture here talking about coupling and splitting. Once we get through that, we'll do another one of those workbook problems. So as you see in our two compounds that we had come up with, the ester and the ketone, I've just labeled now these signals triplet and triplet, and then for the ketone, quartet, singlet, and triplet. So what we want to understand now is, the ester has these two unique sets. The numbers under here, the 2 and the 2, that's the integration. That signal accounts for 2 hydrogens each. But we saw empirically that looking at the neighbors and applying n+1, now we get this splitting of the signal. So we get this triplet. But why does the triplet have these intensities? So for example, if I draw this line, then I draw that line, you could count the distance of these little rectangles going up. So if this was an intensity of 1, that would be twice the height, and then that would be 1. Where does that come from? And then the other thing is, you have this, there's an odd number of lines, right? There's 3 lines in a triplet. You have a distance between the lines. So there's these 2 distances. It's kind of tiny, but this little baby distance there and there. So we want to understand not only the intensity of the lines, how high they are, but the distance between those lines. And again, that all comes back to why the NMR experiment exists, this nuclear spin. That's what is being detected. So there's, we have on here, we have a singlet, a triplet, a quartet. We'll walk through all of the fundamental ones that we need to know and understand why the neighboring spin gives rise to this multiplicity, is the word I'll use. So you can look at a structure, you can count the unique sets of hydrogen, you can find the ratio, and then now you can look at the proton NMR data, count the number of signals, figure out the integration. But now we want to dig a little bit deeper and understand how the neighboring hydrogens affect the way that a signal looks. So this was the n+1 rule, and really, where does the +1 come from? Why is it that? So our first column here is the number of neighboring hydrogens. So that runs through 0 to 6. You get into a situation where you can't have like an unlimited number of neighboring hydrogens, right? I mean, you're limited by the hybridization of the carbon and then what's attached to it. So for 0 neighboring hydrogens, n plus 1 is 1. We call that a singlet. And the signal intensity for a singlet it's got to be 1. There's only a single line. If you have 1 neighboring hydrogen, the n plus 1 rule says you should have 2 lines, and we call that a doublet. So you have 2 lines. In the ratio of those lines, the heights is 1 to 1. It's equal. So that should make sense. But now when we get into 2 neighboring hydrogens, 2 plus 1 is 3. That's a triplet. We have 3 lines. Look at their intensity. It's 1 to 2 to 1. Does anyone know the sort of trend that's going on here? You might have seen it in math or geometry at some point. So if you look at the numbers in that signal intensity, the numbers in each row, you see the outer number is always 1, right? Can you make sense of like the inner numbers? So if we look at the triplet, see how it's 1 to 2 to 1? If we take 1 plus 1 from the prior row, so 1 plus 1, that equals 2. Now if we go to the quartet and we see the ratio is 1 to 3 to 1, so what we're going to do is take 1 plus 2, that gets us 3, and then 2 plus 1, that gets us 3. So that's how you fill out the intensities moving down those rows. So that's called Pascal's triangle. So that's an empirical observation. So we still don't understand why that is. And so I'll give you a brief, cheap theoretical argument about why that is. Again, this isn't a math class. It's not a physics class. I'm just going to give you a very qualitative, pictorial description of why this happens. So there's the table again, and now here are, in theory, what those multiplets should look like. So there's the singlet. It has an intensity of 1. The doublet, intensity of 1 to 1. Triplet, 1 to 2 to 1. Quartet, 1 to 3 to 1. Pentet, 1, 4, 6, 4, 1. And sextet, 1, 5, 10, 10, 5, 1. So practically speaking, when you get into these, like the higher, the quintet or sextet or whatever, those outside peaks, as I said, the intensity is like really low. You might not even see them because they're buried in the baseline. So one thing I want to point out, notice for the odd numbered peaks, so like singlet, triplet, they have a center peak, right? But then for a doublet, it's moved. Anything even number, there's not really a center peak anymore. So right here in the middle, that's usually where the chemical shift for the entire signal is reported. For an odd number, it's reported at the tallest line. And then as I mentioned, after your spring break, when we come back, the other thing we're going to look at is this distance, the distance between the lines. And that's given the notation J. That means coupling. So it's called a coupling constant. So doublet, triplet, quartet, that distance, J, even though it says constant, it can vary depending upon what structure you're looking at. So it can vary from 1 hertz to, say, 15 hertz. So it all depends on the environment in which the hydrogens sit. Any questions? Maybe one thing I can point out, when you're looking at this signal, you say, okay, I see a singlet. What is that telling me? It's telling me there are no neighboring hydrogens. Now, keep very clear in your mind, a singlet can be 1 hydrogen, it can be 2 hydrogens, it can be 3 hydrogens, or it can be more based on symmetry. The integration or ratio is completely different than the number of neighbors. Again, what you can infer from like a doublet is that there's only 1 neighbor. It's telling you the neighbor. It doesn't tell you how many hydrogens belong to the doublet itself. So why is it n plus 1? And this is my very rudimentary explanation of this using some colored arrows or vectors to explain why the neighbors affect any given signal. So again, it has to relate to nuclear spin. And remember that, it's 1H or carbon-13. You have to have an odd number in the nucleus to have the spin. And the way that the NMR experiment works is you have an external magnetic field. So if you've taken physics, that B sub 0, that's the vector for the magnetic field. And nowadays the magnetic field is basically generated through a superconducting magnet, which is like copper wire that's chilled to almost absolute 0, and that forms a magnetic field. And you can't see it obviously, but it like, do you know what a torus is? The shape called a torus or a donut. You like Shipley's or Krispy Kreme, just like a normal donut. That's what the magnetic field is. It's like these opposing sort of circles that run in 3 dimensions. So that's the magnetic field. The nuclei themselves, when they spin, they generate a tiny magnetic field. And that's what's shown here as these blue arrows. So for proton and carbon, you can have 2 spin states. So I'm going to say spin aligned or spin up. However you want to think about it. Or spin opposed and spin down. And that just means that magnetic vector relative to the external field. So do y'all know what a vector is? Say it again. So yeah, it's something with a direction and a magnitude. So it's got to have both of those things. So that's what that bolded blue means in like the vector notation. So if you look at that red arrow, it's pointing up, and then you have spin aligned. So those two vectors would add together, right? The little tiny nuclear magnet would add to the big magnet, and then you'd get a bigger overall vector. The spin opposed is going to subtract. And so the difference between them that's the energy difference. And so we saw a couple days ago, maybe Monday or whatever, the operating frequency in radio waves of the instrument, the 60 megahertz, 400 megahertz, 800 megahertz. So you have this field strength. As the field strength increases, that energy gap increases between the spins. The radio frequency is the energy that flips the spins from one state to another. And then as they relax, that's the signal that's acquired. A bunch of math happens, and it spits out the thing we read as a spectra. But the take-home point of this is you have two spin states, and that is what leads to the n+1, and that is what leads to the intensity difference of the signals we see. So if you want the mathematical description of this, you need to take like calculus, differential equations, physics, and all of that stuff to understand like the theory behind it. This is just very qualitative. So let's look at the situation where, when you're doing the uniqueness test just visually based on a structure, you're saying, okay, there should be 3 unique sets. To a first approximation, they should all be singlets because you're just assigning, okay, it's a set. But now, due to the neighboring spin states, you have to do that second approximation. So if your signal of interest, that's what we're looking at here, if that has one neighbor, what happens is that signal gets split by the spin states of that one neighbor. The one neighbor has 2 spin states, up or down. And so if it's spin up, so that would be aligned with the magnetic field, that little part of it is now more downfield than the original signal. Then you have a spin down, which is opposing. And so now it's more upfield. So I don't want to get these ups and downs. So that the spin that is aligned is downfield. The spin that is opposed is upfield. So notice what I said about chemical shift, like this line here. So that would be that line. It's like you're taking that line and you're sort of pulling it, ripping it apart. A little bit goes to the left, a little bit goes to the right. And that is due to the spin states. So that's where the +1 comes from. Because there's only 2, notice the height here. Intensity, it's 1-to-1. So we know now that the up or down spin states lead to the +1, but then once we get to a triplet, why doesn't a triplet look like this, where the heights are just the same? Why is the center height, double the outside ones? So I use this term here, which kind of always fascinates me about teaching organic chemistry. I say the information is communicated. So I'm verbally communicating to you now stuff is happening in your ears, it's being relayed to your brains, and neurons are firing and stuff. That sort of same process is not happening here, right? It's like these things just know. So through quantum physics or mechanics, the information is transferred. It knows or senses or feels it, however you want to think about it in your brain that makes sense to you. So let's see if we can do the same thing now. Again, I don't have it here, but there's our first approximation. And now we say, okay, that signal has 2 H neighbors. It's leading to a triplet. How do we explain why the center peak is twice the height? So the way that we're going to do that is, remember, each hydrogen can be either spin aligned or spin opposed. And so you're just running through the possible combinations of how that is now. So we say to the left, that's downfield. Those were the spin aligned ones, right? So those have to both point up. For the upfield, they're spin opposed, so they need to both point down. Now for the center one, we're saying that center line is twice the height. So what do we need to write for the center line? So you have one up, you have one down, but then you also have the other possibility of down and up. So see how it's now 1 to 2 to 1. So the spin states help explain the intensity of the lines that you see. And I said, see this distance here of these lines? You have 3 lines, and then you have these 2 distances. Those distances are the same. So from the center peak moving to the left or the center peak moving to the right, that's the same distance. So say, for example, from the center to the left, it's 5 hertz. Then from the center to the right, it also has to be 5. What is the reason for that? The magnitude of that distance, as I said, it changes based on the molecule. It's dependent upon, you have the hydrogens of the signal you're interested in, then you have your neighbors. And we said way back in module 1 that like between a carbon-carbon sigma bond, there's free rotation, right? So look at my hands. Like if these are 2 hydrogens, the angle between them now is 0. If I rotate, it's 90. For every angle, that magnitude of those distances changes in the signal you see. The reason for that is how that information of spin is communicated. And so there's a curve, a mathematical curve, that was the basis for a Nobel Prize, actually, in chemistry, that describes why that is. So as the angle changes, the fierceness or forcefulness of the spin information is changing back to that original peak. you get these angles where it's really strong and the distance is big. Then the angle changes and the distance shrinks. So again, we'll cover that March 10th or whatever. But that concept leads us into Module 3 when we actually start talking about conformational analysis. So there's the pictorial of it. Again, we have aligned, opposed, and mix and match. So now what about the quartet? We said the ratios were 1 to 3 to 3 to 1. The ones are straightforward, right? They're either aligned or opposed. So up, 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 down, down, down. And then you'll see for the two center lines, notice that line in the middle, we still have to obey this down field and up field. So that the taller line closer to the center there, that's downfield, we're going to have two of those spins going up. So up, up, down. And then we're just going to move the down spin so it's in each position. So up, down, up, down, up, up. And then you can see that corresponds to the 3. So for the upfield one, we now need 2 down and 1 up. And then we just move the up one along. So down, up, down, up, down, down. So again, those are spin state combinations. Questions? So here's that diagram showing those little vectors again. You can always keep in mind there's that big external magnetic vector and why you're getting these shifts either downfield or upfield. Any questions on that? So here's another problem from that workbook. So we have IR, mass spec. We have the carbon NMR. Again, that's showing you the normal looking carbon, then above it is the stacked spectrum with the depth. And then we have the proton, and then the numbers in red, it says 9 millimeters. We're going to use that to calculate our ratio. So when you look at the IR, does anything stand out? So this right here looks like an OH. So I'm gonna say this is 1700. Is that right? No, excuse me, 1800. So that's 1600, we see that. If you notice in there, there's something at about 1600, but there's really nothing at 1700, and that's where our carbonyl stretch would be. So there's no carbonyl stretch in there. So we can completely eliminate any functional group containing a carbonyl. So right now what we have is OH, we have an alcohol. So we're going to start looking at the other pieces of data to see what we can tease out of there in terms of fragments. When we see the mass spectrum and we look at the parent ion, does anything stand out about the parent? We have a mass of 172 and it says another mass at 174. So you have M and M plus 2. And then what can you see with your binoculars about the ratio of those signals? So it's 1-to-1. So trust me, even though it might not be resolved, those two signals are 1-to-1. So that tells you there's got to be a bromine. So at this point, it's again like choose your own adventure. We could either, take the 172, subtract off 79. That's the bromine contribution. We could then subtract off 16. Then we get the remainder for C and H. So we could do that, but we're going to take a more visual approach and look at the carbon right now. So let's look at this carbon NMR, the proton decoupled one. We're going to ignore the solvent. How many signals do you see in the carbon NMR?
6.
We see 6 unique carbons. And you would arrive at the same thing again, just to show it real quick. If you took 172 minus 79, so that's Br, minus 16, that's oxygen, you're going to get some number. That's going to be your C plus H count. You would arrive again at 6 carbons. You see the location of those carbon signals? What hybridization are the carbon atoms? sp2? So we're at 80, this is 100. So we start at about 110 and we have something about 150. So your SPs are typically like 80 to 110 maybe. You have something at 110. You have something at 150. But they're all sort of clustered from that 110 to 150. They cannot be sp3. They're too far beyond the sp3 region. SP could be a little ambiguous, but sp2 is we'll run with that. So based on the region they're in, if they're sp2, there's no carbonyl, right? Because we know that from the IR. You also know by looking down here, you don't see any signals. So there's no carbonyl sp2 hybridized carbons. So therefore, what functional group do these have to belong to? What other functional group has sp2 hybridized carbon? Alkene. So that's a good starting point. So a carbon-carbon double bond. So we have 6 signals. Now let's look at the depth. We said anything that was above is phased positive. Anything below is phased negative. There's no signals below, right? When you see how these are stacked. When you look from the bottom to the top, how many of those 6 have signals on the top? 4. So it's telling you that these 2 here, the outer ones, since you're not seeing a signal, they have no attached hydrogens. So that should make sense because we already saw we have an OH and a bromine. So those carbon atoms have to be bonded to those 2 functional groups. Then we're left with 4. And based on the region they're in, see how it says for positively phased, they can be CH3 or CH. Of the 4 positively phased ones, what do they have to be? They have to be CH groups. So we already said they're sp2 hybridized, right? So that you can't have 3 hydrogens on an sp2 hybridized carbon. So therefore the logic tells you they're CH groups. So you have 4 CH groups. Now does the proton NMR jive with that? So notice it says each integral is measured to 9. So how many signals do you see total? This thing over here, this is just a blow up of that region. So 1, 2, 3, 4, 5. See this one, it says exchanges with D2O. So that's your OH group. So OH exchanges to OD, deuterium. So we've assigned that peak. So we got 1 of the 5 done. We have these other 4. Notice the integrations are all 9 millimeters, right? If we take 9, divide by 9, we get 1. So that's telling us each of those integrates to 1 hydrogen. So 1H, 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 1H. We already know OH is 1H. So what do we have? If we put this all together, we said we have 6 carbons. 1, 2, 3, 4, 5 hydrogens. We know from mass spec there's a bromine. We know from IR there's an oxygen. So how many degrees of unsaturation will that molecular formula have? So C6, bromine's going to add, so that becomes H6. Oxygen does nothing. So for 6 carbons, if it was saturated, we should have 14 total hydrogens. So C6 minus H6 That gets us H8. So 4 degrees of unsaturation. So here's another sort of intuition thing that you'll develop. When you start having a lot of degrees of unsaturation, like 4, and then you see the regions in which these signals occur. So these were sp2 hybridized carbons. Notice in the proton NMR, this region here, so like 6.5 to like 7.5. Do you remember from that chart what type of hydrogens those could be? We already said that the carbons have to be alkene-like. We have 4 degrees of unsaturation. So that's the aromatic region. So aromatic, it's a benzene ring. I'm going to move over onto a blank slide, and so we can have some room to work with here. Now look at those 4 signals that you're given. You're deciding now between the 1, 2 and the 1, 3. So the data matches which one of those isomers the best. The 1, 2. So why is that? What's not there? A singlet. There's no singlet there, so it has to be the 1, 2. What you'll notice here is you see that little at the top of those, there's a little bit of splitting there. It's kind of beyond this course, but you see this looks like a doublet, right? You have a little bit of splitting at the top. What can happen is that you have your neighbors doing the coupling, but on another level, the neighbor's neighbor can also couple. So that's what that little bit of splitting is for. But overall, you see the general shape. You have a doublet, a triplet, a doublet, triplet, doublet, triplet. So that confirms the 1, 2. We can reject the 1, 3 because there's no singlet. And I hope that this problem illustrated to you. So we have C6H5BRO, 4 degrees of unsaturation. Carbons are sp2 hybridized. There's 6 of them. Notice all 6 were unique, right? Because we saw the 6 signals. We have OH, we have BR, so 6 of them, 4 of them are CH. So let's start with a benzene ring. So we have a benzene ring. We have these 2 substituents, OH and BR. We have to attach to it. How many different constitutional isomers can we propose from those 2 substituents bonded to the benzene ring in terms of their relationship to one another? there can be 3. So again, we're going to plug those fragments onto the ring. So I'm going to call that a 1-2 relationship. I'm going to keep the OH constant. I have a 1-3 relationship. I have a 1-4 relationship. So we have 3 possibilities. How do we narrow it down? So the first thing we'll do is we'll do a uniqueness of carbon for each. How many unique carbons does the 1,2 isomer have? 6. Every carbon is unique. What about the 1,3? 6. What about the 1,4? 4. Why is this one different? See this line right here? It has a plane of symmetry. That carbon's unique. These are the same type due to the mirror plane. These are the same type, and then that's unique. So 1, 2, 3, 4. We already said by looking at the carbon NMR, there was 6 unique carbons, right? So we can eliminate the 1,4 as being a possibility. In the proton NMR, we saw there were 5 unique signals, right? So let's do the same exercise here. How many unique signals should the 1,2 isomer have? 5. So including that H of the OH, 1, 2, 3, 4, 5. What about the 1,3? 5. 1, 2, 3, 4, 5. Just so we can say we completed the exercise without leaving anything out. The 1,4 should have how many hydrogen sets? 3. So 1, 2, 3. You see we're sort of stuck now, right? Because they both have the same uniqueness set of 6 and 5, which matches the data. So what do we have to do now? We have to dig a little bit deeper and look at the couplings. What's constant between, we already eliminated the 1,4. What's constant between the 1,2 and the 1,3? That OH group is not going to help us. It's going to be a broad singlet no matter what, so we don't have to worry about it. Let's walk around the ring for each, then we'll go back to that data, and then we'll make our final decision. So if we look at this hydrogen here, maybe I'll draw it in blue so it's different. That hydrogen, how many neighbors does it have? It has 1, so what should it look like? So I'm just going to write a little d above it. Now this hydrogen next door, how many neighbors does it have? 2, so it should be what? Triplet. This hydrogen here has how many neighbors? 2, so that should be a triplet. And then finally, the last hydrogen should be what? A doublet. Let's do the same for the 1,3 isomer to see if we can now differentiate. Is there a difference, or is this going to give the same patterns? So the hydrogen here, that should be what? A doublet. This hydrogen, triplet. This hydrogen, doublet. And now what about this one? Singlet. So there's our difference. That's how we can rule one of them out and then confirm the other. So let's hop back. When you get to this issue right here of uniqueness, we ended up with having the same set, right? 6 and 5. So we had to go down another level of analysis to see if anything was different at that point. So these are just the summary slides of what we just went through. Again, here's your 1, 2, your 1, 3, and your 1, 4. So if you're satisfied with my teaching ability in this class and you decide to take Organic 2 with me, Organic 2, we will study the chemistry of aromatic compounds. So if we start with benzene, so C6H6, say we want to make one of these. How are we going to make them? You have to control where you put those substituents. You want to make the 1, 2. You do not want to make anything else. So everything that you've learned about functional groups, resonance, induction, NMR, all of that comes into play. The point of synthesis is we want to make one thing only in the highest yield. We don't want to make little byproducts that erode our yield. And so this is the method you use to make your claim. So we've positively reinforced the claim in a way through the absence of other signals. We've rejected the 1, 3. So here's a summary of all of that stuff with the relationships, the uniqueness of carbon, proton, the ratios of the hydrogen sets. So I'll tell you right away, when you're looking at spectra or you're doing research and you acquire your own spectra, the 1, 4 is the easiest to spot immediately because in the aromatic region, you're only seeing 2 unique sets. So it's pretty easy to reject the other ones. And then for the 1, 2 and the 1, 3, that's when we went around the ring. For each signal, we looked at the neighbor, we assigned the multiplicities. So we said doublet, triplet, triplet, doublet, doublet, triplet, doublet, singlet. And that was the criteria which we compared. So this gives you a summary of that analysis. Again, I like to put things in tables to help see trends and whatnot. And a student absolutely eviscerated me on my course evaluations one year by saying, just throws up these tables and I can't make sense of it. So that's the way that I learn these things best, because I can compare and see similarities and differences. It's your learning, so I would encourage you however best you feel making this comfortable for yourself, sort of put it in that learning tool, whatever works for you. But given that, organic chemistry is a lot about structure, I encourage you to draw things, write down little notes. Try to get the stuff out of here as much as you can down onto the paper. The less stuff you're trying to compare in your mind, the easier it will be for you to arrive at a conclusion. So I think that's the last slide. Any questions? So that Notre Dame website that's on Canvas, you'll find problems similar to this. It's just the data is shown to you in a different way. I would encourage you to go through those and practice this stuff so that you get the skill and the intuition down and you start seeing the patterns.